Position 1 is straight bar. Position 2, it's a bar, a vertical bar, right? Okay, so those are the two positions for this problem. And this problem is pretty obvious since everything is released from rest at position 1. That means no kinetic energy at position 1. And what is going on at position 2? Do we have velocity? Of course, because this problem is asking us to find out what is the speed of particle at position 2. Okay, once you know position 1 and 2, you can start to set up the solution for this problem. So I will skip step 1 all the way to step 5. I will leave that for you to do. Here, one thing, since step 1 is quite important, right? If you messed up step 1, and you messed up everything. Free body diagram, it's one of the most thing for this chapter. So here's a trick. When you do free body diagram, usually the a good way to do that, it's based on, let me see here. It's the best way to draw this. Here we have two positions. I would draw my free body diagram. How many forces should be on the free body diagram? And the question here may be, we have two positions. Does that matter if you draw your free body diagram based on position 1 and position 2? Or maybe other positions in between? Would that change your free body diagram? Okay. So if we draw the free body diagram at position 1, how many forces going to be on your free body diagram? We already know one force that is given in this problem. It's perpendicular. That force is normal to the rod. And what is going on at point O? The whole rod is pinpoint at point O, right? And what is the force should be? Should we have a force there? Yes, we should have a force at any support. Let's call this force R. This is point O. What other forces we should have? Just a particle then. Because in this problem, this particle is attached to that rod. So there are other forces on that rod. So if you can think about this particle and the rod as a single rigid body. But all the mass is applied on the particle. The rod is lightweight, so there's no mass, but all the weight is in the particle. That's a good question. Okay, so our particle should have a weight force. Those are the three forces you should have on your free body diagram. So it doesn't matter which angle that rod is, you should always have three forces on your free body diagram. Okay. All right. So Then let's jump into steps 6. Set up tables for kinetic energy, T. So T1, T2, based on the masses. We only have one mass here. Things should be pretty easy. So at position 1, it's just 1/2 mv squared. That's, make sure you label that as V1. It represents the velocity at position 1. Like I said, that's position 1. So go to your sketch, look at position 1, read the problem again. What is going on? It says released from rest. That's a sign, tells you 0 kinetic energy. So here, T1 at position 1 is 0. Kinetic energy at position 2 is something we're trying to solve. We don't know what is V2. So just write there as V2, 1/2 mv2 squared. Okay. Since we only have one mass here, so we're done with step 6. Step 7, potential energy table. That's V1, V2. Okay. We talked about we have 2 different types of potential energy. One is from gravity and another one is from spring. Do we have a spring here? We don't have any spring, so all the potential energy is going to come from gravity, from the weight force. Like we talked about this, we need a 0 reference point to set up our potential energy. So go back to your sketch here, set up where do you want to put the 0 reference point? Okay, where do you want to put the 0 reference point for your gravity potential energy? Anywhere. Depends. Like if where you prefer. I can say, all right, let's do this. This, it's a 0 reference. So at that height, we have 0 potential energy from gravity. This is how I define it. You can put that anywhere, but keep that consistent. So if I define this is my 0 reference level, the height, and at position 1, my particle P has 0% potential energy. Now, what is going on for my potential energy at position 2? So at position 2, yeah, the 0 reference still at the middle. So in that case, particle P is below that 0 reference point, which means at position 2, you're going to have negative potential energy, right? So let's go back to the table to finish this up. At position 1, we're going to have just mg h1, which it's just 0 because it's right at that 0 potential, 0 reference point. At position 2, we have mg h2. That equals mg, oops, mg, we have to find that height. What's the height is given? In this problem, particle P to O, it's 0.6 L. But that length, that height is negative since it's below reference point. So make sure you add that negative here. So negative 0.6 L. All right. Okay. Those 2 steps are not too bad. Next step is going to be a little bit tricky. Step 8. It's all the work done by non-conservative forces. Okay, here I have a question for you. How many non-conservative forces we have? Evan, no idea. One, which one?
I was thinking just the force.
F. You think just the F force? How about this R force? Okay. So we have two external forces, right? F and R in our free body diagram. So let's put there. So we have a force F, we have another force R. Potentially they will do work to the system. Okay, maybe let's look at F. So what is the work done by that force F? What equation to calculate work done by a force is force times the distance that the particle is traveled.
So it'd be the distance traveled in that arc that it's taking.
Someone's talking through Zoom. So yes. So the distance that force applied to that rod, it's the arc from position 1 to position 2. What does that arc look like? Can we draw that? Yes, we can draw that. So that arc looks like, right? That's a very bad drawing, but you get it. It's an arc. It's a quarter of a circle, right? From position 1 to position 2, that F force traveled a quarter of a circle. And how to calculate that arc, the length of that arc? How to
1/2
calculate
pi
the
r squared.
pi
No,
r
1/2.
squared
Yeah.
divided by,
No.
we only have a quarter. It's divided
Yeah.
by 4.
Yeah.
So that arc length, it's pi r squared divided by 4. Okay, so that should be the work done from that force. F times pi r squared divided by 4. Here, substitute our r. What is our r here?
Shouldn't it be pi d?
Yeah.
So here,
Because
the radius is 0.4 L.
isn't that an area, not a length?
Oh, yep. Sorry, my bad. Made a mistake here. That's not the equation. 2 pi r is the equation to calculate the length of the circle. So it's 2 pi r divided by 4. R in this case, it's 0.4 L. So plug that in. That's 2 pi 0.4 L. So we can plug in that into our table. Just F times 2 pi 0.4 L divided by 4. Okay, that's a work done by that force. Okay, that work is positive. Why is positive? Because the force is pointing to the same direction of that distance, right? Of that motion. So it's positive. Now let's look at R. So our free body diagram, we have R. That's a reaction force acting at this point O. So what is the work done by that force R? Noah, do you know answers? What's the work done by that reaction force R? Noah, by any chance? No? No? Yeah. Anybody knows? Bethany?
I think it's 0
Why is it 0?
because the force applied by that is just keeping it like I'm not translating. Like it's Not moving.
Not moving. Yeah, the equation to calculate work is force times distance. Any distance point O travel under that force. No, right? It's fixed point. So here it's just R times 0 distance. Great. Now we have all the force, all the kinetic energy, potential energy, and work done from non-conservative forces. You can do step 9 by yourself outside class. All right. Any questions on this example? All right. Do step 9 outside class, since we're going to move on to the next example. The next example, this one. It's on your textbook 225. Yeah, looks like, wow, what is going on? But if you read the problem, you realize it's pretty similar with the last example. Same thing, we have a rod. The rod is attached to a particle, but in this case, we have two particles, one on each side, each end. So we have particle A, particle B, and this is a rod. And the rod is attached to them. So when you draw free body diagrams, you should draw the free body diagram for the whole rigid body, which is that AOB. Right. Now, what is different here is we have a spring down there. So let's read this problem. Okay, so from here, this system is released from rest at position 1 with theta equals theta 1. Theta 1 is given down there. And with A in contact with a pair of identical springs. So it's the position 1. The drawing here is position 1. So that theta 1 equals 36.87 degrees, and that particle A is in contact with the spring. Okay. Each spring has a stiffness. The stiffness means the spring constant K. So that's the same thing. K and the spring are unstretched when theta equals 0. Okay. Make sure you understand what is going on here. So springs are unstretched when theta equals 0. That means when this bar is totally horizontal, then there's no contact between the ball and the spring is unstretched. So assume the dimension of the particle is negligible. We're trying to find the speed of A and B at position 2. We're in position 2, particle A, it's directly above O. So this problem is pretty nice. I already did the sketch for you. Position 1 is right here. Position 2 is when this bar is straight vertical, when particle A is up there. Let's make sure we label that as particle A prime, B prime. Okay. Now, I want you to think about how to draw the free body diagram for this problem. Okay, we have two positions. In this case, the free body diagram gonna look different at position 1, position 2. So at position 1, you're gonna have the weight force coming from this particle and weight force at this particle. You're gonna have a reaction force at point O. And also we have a spring. That spring is compressed at position 1. Once again, that spring is compressed at position 1. That means what? That means there's a spring force going up, acting on that particle A. So at position 1 in your free body diagram, you will have a spring force. But what is happening at position 2? Nothing is in contact with the spring, so there's no spring force. Right now you have to make a choice. All right, should I draw my free body diagram based on position 1, position 2? So a suggestion here is look at in which position you're gonna have the most forces on your free body diagram. So in this case, position 1 gonna have more force, which is that spring force. So we're gonna draw our free body diagram based on position 1. Questions?
So is position 1 not at theta equals 0?
Okay, let's read this again. At position 1 with theta equals theta 1 equals 36.87. So read the problem carefully. All right. Now let's draw our free body diagram. It's gonna have 2 balls, reaction force R, weight force B, weight force A. Also, we're gonna have a friction, spring force going up, acting on particle A. It's gonna have Fs here.
So the reaction force isn't angled at all?
It's what?
It's not-
The reaction force R
Yeah.
is just gonna be just pointing up, straight up. If you have a pinpoint, just assume that reaction force is straight up.
Okay.
Okay, that's the free body diagram. Then I will leave step 1 to step 5 for you to do that. So let's start from step 6. Kinetic energy table. How many masses we have? We have 2 masses. We're given 2. So make sure you label them as MA and MB. So at position 1, if you read that problem carefully, you will notice the word release from rest. So at position 1, both 1/2 mv. All right, here, once again, we have 2 particles. The 2 particles, they don't share the same speed. So make sure you differentiate them. So here we have particle MA VA1 square. This equals to 0. For particle B, we have MB VB1 square. This equals to 0 too. Now let's look at kinetic energy at position 2. That's something we're trying to solve. We're trying to determine the speeds of particle A and B at position 2. So this is 1/2 MA VA2 square, 1/2 MB VB2 square. That's it. That's all the kinetic energy you should have on the table. Step 7, tables for potential energy, V1, V2. We have 2 different types of potential energy, right? One's from gravity, weight force. We have 2 weight forces, weight force for A and weight force for B. And we have 1 spring. Okay, at position 1. All right, yeah. Before we do this, you must set up where's the 0 reference point for your gravitational potential energy. So make sure you label that on your diagram, on your sketch here. So here I like to no. Let's make, which point do you like to make that as 0 reference point? Sometimes it can simplify your calculation. So if I set up here as my 0 reference point, then I'm going to have potential energy for both A and B at position 1 and 2. But if I set up this point at position 1 as my 0 reference point for potential energy, this particle A is going to only have 0 potential energy at position 1. So I can put a 0 there. So where you set up your 0 reference point can simplify your solution. Are we experiencing earthquake? Do you see the vibration on the projector? Okay. All right. Anyway, let's get back to our table. I will set at this point as 0 reference. Okay. In your homeworks and exams, I want you to label where you set up your 0 reference point. Okay. Now we're going to talk about potential energy relative to that 0 reference. For A, at position 1, you're going to have MAGHA1, which is 0, because I set that point as 0 reference. For our particle B, we have MBGHB1. What is that HB1? We have to calculate what is that height. What is that height here? That's HB1. We know the angle theta. So this angle is theta. We can build a triangle. This angle is theta. Inside of that triangle, we know the total length of the rod. It's L plus 2L. And we can use sine theta to find out what is the height HB1. So that HB1 equals sine theta times L plus 2L. Okay, but I don't have the space to write that down in my table, but you should. Okay, now let's look at what is the potential energy for A and B at position 2. At position 2, so my A is up there all the way above point O. So that's pretty easy to calculate. The height here, it's HA2 equals 2L plus that distance here we have to calculate, which is sine theta times 2L. It's not just 2L as the height, but we have to consider this small height here, since we set our 0 reference point below point O. So the height is 2L plus sine theta 2L. Okay. So here it's MAGHA2. For MB, we have MBGHB2. So for B2, it's the same here. It's a distance from the reference point to particle B. In this case, it's going to be easier. Nope. It's going to be L minus sine theta 2L, right? Because part of that, the length of the rod, is here. So we need to find out this height instead of that height. So we need to use that minus what is the length here. So it's L minus sine theta 2L. So there's some calculations about height you have to do based on where you set up your reference point. Okay. Now we're done with potential energy for A and B. Now let's deal with the friction, the spring force. So spring force Fs at position 1. At position 1, the spring is compressed. So we have 1/2 K delta x1 squared. At position 2, it's unstretched. So I have 0. How to find out that delta x1? Do we know the original length of that spring? Okay. We know K though. We don't know that length. Okay, so that's something we don't know. All right. Step 8 is to find out all the work done by non-conservative forces. In this case, we only have the force R, which is doing 0 work. That point is now moving. Okay. And once you have those 3 tables, you can assemble the work energy equation to finish up this problem. Okay, so here's a trick. Let's look at how I set up my 0 reference point. Here I set up this 0 reference point for potential energy at here. I set up this as for the whole system. So everything's it's relative to that point, right? But to simplify your calculation, well, if you're the person who is above, on top of the class, want to simplify everything, get things done easy, and you can use 0 potential energy, 0 reference point for particle A, and use another one for B, and you will get the same solution. So imagine if I set this only as a 0 reference for my particle A, and if I set up here as my 0 reference for particle B, then when I do my potential energy calculation, my VB, my potential energy for B at position 1 going to be 0, right? So I have less calculation to do. But that would change what's the potential energy for particle B and A at position 2. So at position 2, the potential energy of A is still going to be mgHAA, the height from there to where we set up the 0 reference point for A. But for particle B, it's going to be from this point all the way to here. So the height here is all the way from here towards the position of B at position 2. So depends. if you're very good, you keep track everything, you feel free to do this method. But if you're not, I won't suggest you to use this method. Just use one single reference, zero reference point for your whole system so that you won't make mistakes. I will erase this. But you get what I'm saying? If you have multiple masses, you can set up zero reference point for each single mass to simplify your calculation. All right, any questions on this example? Okay. If not, let's look at one more. We have 5 minutes left. Oops. How about this problem? So we have a particle P. It can move freely along a fixed, smooth, curved rod. Smooth, that means no friction. And from position 1 to position 2. So a label here, position 1 is right here. Position 2 is up here. And we know this particle, there's a constant force, F equals 20 Newton tension force in the cord. So that's the tension force in the cord. Here, the tension force, you can think this as a pulley. So it changes its direction. Even the force is pulling down here, but this pulley here changes direction. So what the force acting on the particle P, it's along the cord, has the same direction as a cord. So we want to determine what is the speed of the slider at position 2, which means it's the speed of particle P. Everything is released from rest at position 1. So let's set up what is a free body diagram? That's step 1. Got particle P. We have a weight force. And depends on the location of that particle P, you're going to have a tension force from that cable, from that cord. And the magnitude of that force is F. And on that particle P, you're going to have a normal force. And that normal force is always normal to that slide. Here you cannot have 3 forces. That force F is going to be a troublemaker, right? Since anything we know about that force, so that force, it's a constant force. So that force has constant direction. It's always pointing in that direction. Can you imagine that? Even this force is acting on the same direction, but the force here is always changing because it depends on where the position of that particle. It's keep changing. But this force here is acting at the same direction. So that's step 1, set up free body diagrams. And the tricky part of this problem is at step 8. So I will just jump all the way to step 8. So when you need to set up, what is the work done by that force from 1 to 2? Non-conservative force. You have to calculate the work done by that force. The equation is F times S, right? The tricky part is how to find that S, the distance S. If you look at that problem, easier to think about, okay, if you have a cable and what is the length, the change of length of the cable from position 1 and position 2? Since that change of the length of that cable, it's how much that cable is pulled by that force. So you have to find out, kind of twist your mind, bend your mind, think about how the length of that cable is changed. The change of length, it's the distance where that force applied to that cable. Because here, this cable force is continuously pulling that cord at the same direction. So you have to do trigonometry to find out what is the length. Okay. All right, so that's all we have today. We did 3 examples. That's pretty good. All right. Make sure to start your homework early. Ask questions, like always.